All right, so unit 4 was linear momentum. In this unit, some of the main concepts were just conservation of momentum, and where we looked at different collisions, whether a collision was an elastic collision or an inelastic collision, and whether or not kinetic energy or energy as a whole was conserved, or whether momentum was conserved, which in any collision, momentum is always conserved. And then some of the other units we talked about were
Which one? The integral definition?
yeah.
Oh, so what was new to us was the integral definition of the center of mass. So it's like x center of mass equals 1 over m, the integral of r dm. And this is where, which was also new to us, where we brought in like lambda, omega, and I forgot the other one, but lambda's for linear, omega was for rotational. And based on that, like for example, lambda equals dm over dx. So if it was a linear collision, then the question would probably give us lambda, and then lambda dx would equal dm, and we could plug that into the integral and use that to help us find the center of mass. So that was new to us. Didn't really struggle with that, but I thought it was really interesting. It stood out to me, and
Yeah. Were there any other concepts that you kind of talk about?
we did rocket science, no?
Yeah. Rocket science, that was just like where you had the jet propulsion, and you had it push out mass very fast at a high rate. And since that side has a new mass and velocity, the other side would have to have the same to account for that in order to conserve momentum. So we just learned that that's what propelled the jet. But yeah, I think that's some of the main concepts from this unit. All right, so the problem that we're going to attempt to do is to find the center of mass of a sine, and I'll put the problem right here, and I'll go ahead and draw it out. So basically, we have a sine, right, and we're asked to find the center of mass, so we can put like a metal wire, which will be able to hang up the sine, where the bottom will be directly parallel to the ground. All right, so in this case, we know that there's a theta value. We also know that there is some value x, which is changing, and there's a respective value y that changes with x. It also tells us, it gives us a little sliver of this mass is going to be equal to dm. And then it gives us that the whole base of this triangle is a, and the whole height of the triangle is b. And then lastly, the hypotenuse is c, right? So we're asked to find the center of mass. So we're going to use our equation for center of mass, where the center of mass of a rigid object with shape is 1 over m, the integral of r dm, where dm is the change of mass. Okay, so the first thing that we should do when we approach this type of problem is to try and find out which equation we should use to substitute for our dm. In this case, since we're dealing with area, we're going to use omega. So we're going to say omega is equal to this tiny change in mass over a tiny change in a. Since omega is just m over a, we can just say it's equal to dm over dA. Now, like I said earlier, it gives us this dm value right here, which is this tiny sliver in area. It's good, Steven. And so right now we're going to try and solve for dA, or we're going to try and solve for dm. That way we can substitute that this dm value into our integral. So we'll say omega dA is equal to dm, right? And dA is just the tiny change in area. For this case, this tiny change in area is going to be a rectangle, and this value is going to be equal to the height, right, times the dm value, because it's going to be a rectangle. So the width is dm, this will be dx, not dm. It'll be the tiny change in width times the height, right? So we'll say dA is equal to dxy. So omega y dx is equal to dm. Substituting for dx, we know, substituting for y, we can also say that tangent theta is equal to y over x, right? Because we have a theta value right here, tangent's opposite over adjacent. We multiply both sides by x. We can say that y is equal to x tangent theta. If we plug this value in for y, we'll get omega x tangent theta dx is equal to dm. And finally, we can plug in our dm value. And we could set r equal to x. So I'll go ahead and rewrite this equation. X center of mass equals 1 over m. The integral of x times dm, which is omega x tangent theta dx. Okay, you pause it. Okay, as we continue to simplify, we can say x center of mass is equal to 1 over m. We can multiply out this x because they're the same. So x squared omega tangent theta dx. What we can also do is we can pull out this omega and tangent theta because, as I said before, omega is equal to mass over A. This mass over A is of the entire rigid body, so that's a constant. And tangent theta is also a constant. Y over x will be the same ratio no matter where you are, no matter where you put it. And we also know that theta is going to be the exact same value. So we can take both of those out. So x center of mass equals 1 over m times omega times tangent theta times the integral of x squared dx. If we substitute back ma, we get x center of mass equals 1 over m times m over a times tangent theta integral of x squared dx. These m's cancel out, so we just get x center of mass equals tangent theta over a. And our bounds for this integral is, since it's dx, we know that it starts at 0 and it's going to end when x is equal to a. So we can say our bounds are from 0 to a. Keep in mind these a's are different, so I'll just notify this with a lowercase a. This is the area and this is the horizontal distance. So we'll say x squared dx. We take the integral, x center of mass equals tangent theta over a times, we do the power rule, x cubed over 3, a 0. We'll as we continue to integrate, now if we solve for area, we'll get the area of this triangle is going to be equal to 1/2 length times width, right? So 1/2 a times b. So we can go ahead and substitute that. Since 1/2 is in the denominator, we'll put it to the numerator. So 2 tangent theta a times b times this a cubed over 3. Take out an a, this becomes a squared. So we have x center of mass equals 2/3 tangent theta times a squared. We also know that tangent theta, right, is equal, y over x is the same thing as b over a. So we can make that substitution right here. We can say x center of mass is equal to 2/3 b over a times a squared, where this a cancels out, this a cancels out, so we'll get the x center of mass is equal to 2/3 of BA. All right, so for Unit 4, linear momentum, we didn't do any labs, so
nothing to talk about.
yeah.